All right. So, where we left off, we were talking about mixtures. So, now we're going to move on to, we talked about some polar substances. We talked about salts dissolved in water. Now we're going to talk about gasoline. And what is gasoline? Does anybody know? Yes. So the answer was it's a mixture of multiple types of alkanes. Primarily, the one you hear of is octane. You hear like high octane. So that's one of the biggest ones in gasoline. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. With all of these having the hydrogen groups. Now, if we look at this molecule, what do we know about what sort of intermolecular forces this would have with other molecules of the same type? I'll just dance and wait. I'll ask another question. Is this molecule polar or nonpolar? Nonpolar, right? There's no areas of polarity here. So if I have nonpolar molecules, what sort of intermolecular interactions do they have? Yeah, merely dispersion forces, right? So these would sort of line up with other alkanes. I'll just do like a pentane, a heptane. Since there's no areas of permanent partial charges, the only interactions are dispersion forces. So they will make a solution because they're both nonpolar, or they're all nonpolar. All these alkanes are nonpolar. So they'll mix within one another because there's nothing for them to like grab onto specially, right? One octane molecule isn't more attracted to other octane molecules than it is to a pentane or a heptane because they all just have these dispersion forces. They're all nonpolar. So they're happy sort of mixing and mingling within one another. Now, if I put gasoline into water, what's going to happen? Yeah, they won't mix. Let's take a little image of what that's gonna look like. It does, so it looks like a rainbow. So this is neopentane, and so I have these big blobs are, oops, molecule, set clipping center, and son of a gun. All right, so these big molecules, these are neopentane, and the other ones are water molecules. Now, if I just let it play, watch the water molecules. They're just sort of randomly moving around it. There's no area on the neopentane for them to grab onto, so they can't get in there and split the neopentane molecules apart. They'd much rather be with other water molecules than they would with the neopentane, right? So if you don't think about it as likes and unlikes. Actually think about the fundamentals. Water has partial charges. It's going to be attracted to other water molecules. Neopentane does not have partial charges, so there's nothing for the water to be attracted to. So the water is just going to stick with itself, and the neopentane will stick with itself too. Does that make sense? Okay. So as you can see, the water's not getting in between. Oh, I can use this. The water's not getting in between the neopentane because there's nothing for it to hold on to. It's just going to stick with other water molecules. And you can see they're just vibrating around the neopentane sort of at random. All right. Now, I can also show you the hydrogen bonds between water molecules and show you that they're not going to form. Oh, let me, hold on. That's hard to see. Oh, that's much harder to see. Also difficult to see. Yeah. Whoa. Way up close. All right. It does look a little like a caterpillar. All right. I don't know that that's any easier. So you can see all the hydrogen bonds, all the attractive forces are between the water molecules and not the pentane. So the water's going to stick together, the pentane will stick, neopentane will stick together, and they're not going to mix. All right, so we'll pause that. Go back here. All right, salad dressing. What is salad dressing a mix of? Oil and vinegar? Right. I mean, I'm not sure. I don't really eat that much salad. So salad dressing is a mixture of oil and vinegar, right? So we're just going to simplify it. And we'll do, we'll do oil. I don't know, should we do vinegar? All right, we'll do vinegar. All right, so oil. What is oil? What's key about oil? Yeah. It's nonpolar. So oil, oil equals nonpolar. But there's something about oil, it's nonpolar, but it's also polar at the same time. And vinegar equals polar. All right. So I'm just going to draw oil molecules like this, where this is polar and this is nonpolar. So at the head of an oil molecule, there's this polar area, and the tail is all nonpolar. Where do we see this really importantly in biochemistry? Oh, I just want to get a lot of voices. Yeah, Alex. Micelles, which we're actually going to talk about that exact thing in a minute. Cell walls are made up of these lipids, the oil and fat, these bilayers, right? Where they all arrange themselves, the nonpolar parts together and the polar parts together. So, all right, vinegar. HC2H3O2. So the structure for vinegar is this. H3, and then so the question is, why do we put the H at the beginning here when there are H's in the middle? Why don't we just make it C2H4O2? It's in a significantly different place. Also, this H can go away. What's another name for vinegar? Acetic acid. So the H in the front signifies that it's an acid. And what we're going to learn later in the year is this H will actually go away, and you'll be left with the acetate ion and the H plus ion. But for now, we're going to say it all sticks together. So I have this polar. Not only is this polar, but it can make hydrogen bonds. So I have this polar stuff and my oil, which is both polar and nonpolar. So if I have a beaker of vinegar, vinegar is clear, but I'm going to make it like a light blue, just so we can see. All right. So So vinegar, I have mostly vinegar. But now, if I put that oil in there, the oil's not going to want to mix with the vinegar. That nonpolar part wants nothing, well, it's more that the vinegar has no interest in the nonpolar part of the oil. So what happens is the oil particles line up such that all of the tails go together and all of the heads stay on the outside. Polar heads towards vinegar. So they make what's called a micelle. So all the nonpolar tails form in this sort of spherical arrangement where they're all on the inside and the polar part is on the outside. Because the water will be attracted to the polar heads of the oil, but not the nonpolar insides. So this is how this is actually, if you want to talk about energy, this is how they minimize the potential energy. Because you get the nonpolar tails together and the polar heads together. One of my papers that got published, now a very long time ago in a journal, was about using things like this to deliver medicine, right? So you can take something, I'm simplifying it greatly, but you can take a substance that dissolves in nonpolar substances, and you can put it in essentially this particle, like almost like a fat particle. So you put some medicine in the center of your micelle, and then you can deliver it to patients much more safely. Because during chemo, one of the things that really gets people sick, the chemotherapy itself, the medicine gets people sick, right? Because you're giving something to someone that's meant to kill cells, right? So it's not perfectly tuned to killing cancer cells. It also kills human cells, like healthy cells, But if one of the other things is the cancer drugs are not very soluble in water. They tend to be very, very insoluble. So you have to deliver them using things that aren't water, like organic compounds. So you need to use organic solvents a lot in chemotherapy, and our body does not like organic solvents. So our body rejects those solvents and it makes us sick. So if you can deliver drugs within this cell, then when you get into the body, this might open up and deliver the drug with a lot lower amount of organic solvent, right? And for us, we were actually making particles with these embedded in them. And so you can actually utilize that to deliver drugs. Yeah, Edward. How do you spell micelle? It might actually be on the next slide, but it's like Michelle without the H. Yeah, so what we would do, we would make these emulsifications. Remember we talked about did we talk about emulsifications? Yeah, essentially we'd make these colloidal solutions, and then we'd use that to deliver drug. It never got outside of never got into humans. We never made it that far, but the technology is theoretically sound. Okay. How does soap work? Something that we use every day, hopefully. So soap molecules are called surfactants. So not quite. So the suggestion was it makes oil molecules polar. Even sort of better than that. So it does two things. It decreases the surface tension of water. So these surfactants disrupt the hydrogen bonding because, oops, no comma, because they have polar and nonpolar regions. Does anybody know how soap was made back in the day? So you would mix fat and sodium hydroxide, and you'd get essentially what you had in the previous slide with oil, except instead of being a polar head, it would actually be polar. It's like it would actually be ionic on one end. You'd have an ion on the head, and you'd have the fatty tail. If you've seen Fight Club, I don't know if that's what people are smiling about. In Fight Club, Tyler Durden goes to get fat from like a liposuction clinic and mixes it with lye, which is sodium hydroxide, to make soap. And that's why the cover of Fight Club is, it says Fight Club on a bar of soap. So it decreases the surface tension by disrupting the hydrogen bonding, and the soap forms micelles. And the oil/dirt goes into the micelle. So what you'll get is something like this. What color should I use for the micelle? Blue. And all right, so we'll have this, and this is charged. It's probably going to be negatively charged. But it loses it. I'm not sure if it's negatively or positively charged. That's not important. The fact that it's charged, so the water is attracted to it. And then inside the so dirts and oils tend to be nonpolar. That's why using pure water doesn't clean your hands well, right? The Mythbusters did a thing where, was it Mythbusters? I want to say, I saw something about, like, if you just wash your hands with pure water, it doesn't really do that much in terms of cleaning away bacteria and stuff. That's why you have to use soap, because the soap decreases the surface tension, so the water can get in between all the cracks and stuff, but also the micelles pick up the oil and the dirt. So this has everything to do with intermolecular forces and attractive forces and wiping away grime from your hands. All right, solubility of gases. So I think we talked yesterday about how fish breathe, right? So for us, we talk about nonpolar gases should be insoluble in water. And this is true for the most part. However, small amounts can be dissolved. So, small amounts can get in between the water molecules. Concentration in solution depends on gas pressure. So if I up the pressure of something, I can put more nonpolar gas into it. This has this has one legitimately huge impact and one huge impact on my life and maybe the lives of many of you. Yes, so the one that has like the impact on my life and many of you is soda, right? So if you think about soda, I can't drink coffee, so I end up drinking soda. It's awful. All right, so you have a can of, I'll show my brand loyalty. So you have a can of Coke. You open the can of Coke. What do you hear? So it's under pressure. And while it's under pressure, you have CO2 dissolved. As soon as you release the pressure, the CO2 comes out of solution and bubbles. Hiss. That sound. It's not really a hiss, but whatever. I'm not good at onomatopoeia. All right. So that's one that is sort of the less important but still critical to my waking up in the morning. I do. It's my one bad habit. I mean, I probably have other bad habits, but I do drink Coke. I drink a can of Coke on my way in. It's gross. It's awful. Don't do it. But I can't drink coffee. Coffee makes me shake. So, what's that? And I've tried drinking green tea, but that also makes me shake. So, okay. So, what is the one that has a greater impact seriously on our lives? Not beer. Ocean. What the pressure of what gas is increasing in our atmosphere? CO2. So you don't hear it really in terms of partial pressure, and we're going to talk in chapter 9 about partial pressures. But you hear about the increasing CO2 percentage in our atmosphere in terms of parts per billion or parts per million or whatever. So as that increases, oceans absorb more CO2. And this, for a reason you'll learn about in chapter 17 or 18, leads to acidification of the oceans. So as the ocean absorbs more CO2 because we're putting more out, and thus increasing the CO2 pressure in our atmosphere. We're putting more CO2 into our oceans, which is bad because it acidifies our oceans. It's bad because a lot of sea creatures can't handle the changes in acidity, and scary, legit scary stuff. So we talk about global warming being bad, but this is another aspect of man-made global climate change that's terrifying to me, is what we're doing to our oceans by pumping out the CO2. All right. Does anybody need me to wait? Oh, did you have a question? Yes. All right. If it comes back. All right. So we talk a lot about energy in this class. It's like this sort of unifying theme that goes through a lot of what we do. Imagine energy of solution in 3 steps. You have to expand the solute. And what that means is you break the IM forces between particles. Right? We talked yesterday about solutions not having any interaction between the solute particles. So if you take something like salt and you put it into water, that means you have to break apart those ion-ion force intermolecular forces. But those solute particles, they need somewhere to go. So you also need to expand the solvent. So you also need to break some IM forces between solvent particles. So expanding the solute, expand the solvent, and then solution formation. And this would be, in this case, you're making IM attractions between solvent and solute particles. So those are the 3 steps. I think the next slide, though, makes it more understandable. All right. So we're going to go back to our fundamentals on the next slide. I'll wait a few more seconds. All right. 3 steps. Here are the 3 steps. Step 1, I'm taking my solute particles, again NaCl in this case, and I'm splitting them apart. If I have things that are attracted to one another, and I move them apart, what does that mean about the energy? PE increases. So what kind of change is that? Endothermic. All right. How about step 2? I need some holes for those solute particles to go in. So I'm breaking up intermolecular attractions. So what does that mean about the potential energy? PE is going up again. So this is also endo. Now, I'm taking things that are attracted to one another, bringing them close together. What does that mean about the potential energy? Goes down. So this step is exothermic. So if you split making a solution up into 3 stages, 2 of them are endothermic and 1 of them is exothermic. Now, you guys are going to be doing a lab in the not so distant future. Mr. Hamill and I, if you go to the calendar now on my website, every lecture date is posted for the rest of the year. I think every quiz date is posted for the rest of the year. You can see like when we're going to do what. But we're going to do a lot of labs. And one of the labs that you're going to be able to choose from is making a hand warmer. You guys know how those hand warmers work if you go out in the cold, or toe warmers. You hit them together or shake them and they get really hot. What's that? So some of them are metals, right? You snap a metal and you get actually crystallization of, I think it's sodium polyacrylate, sodium acetate. I think that's sodium acetate. But a lot of them are this sort of reaction where you have a solution being made. You have like stuff in a packet. You snap the packet and you have an exothermic reaction that releases a lot of energy, right? So some can release lots of energy, but you'll have some reactions that when you dissolve them in water, they're actually going to be endothermic and get cold. So when we do our hand warmer challenge, you're going to observe some of these. So let's look at the steps. The energetics depend on how much the 2 substances like each other. So if the attractions between 2 substances are greater than attractions with... Guys, talk to your tables and fill this out. I'm tired of talking. Ask that question again. To the whole class. Mm-hmm. Mm. Yeah, hydrochloric acid. Mm. Mm. Mm-hmm. No. Okay. All right. So, what do we think? I haven't been using the cards. We also have to get back and do like a name game thing because I feel like we've lost track of each other's names. So, Wesley, what did you put for this first one? Okay, fair enough. So what are you confused about? Mm-hmm. Okay, so the question was this looks ambiguous because maybe they might not combine together if they have different attractions. But you can like water molecules are attracted to one another. Sodium chloride ions are attracted to one another, but they're also attracted to each other, right? So they don't have the same strength, but they are. So like in water, you have hydrogen bonds between the water molecules, and in sodium chloride, you have ion-ion attractions. When you, that would be for this here. Between would be ion with dipole, right? The dipole of water with the ion of sodium chloride. So if the attraction between the two substances are greater, that means they really want to come together. So what do you think that would be? Yes. So this would be greater, so this would be exothermic. If attractions between the two are similar, then dissolution involves a change of energy, and then this one must be endothermic. Now, there was a question over here. So the question was, if they are endothermic, why are they occurring? Because if the attraction between the two substances are weaker than what they had originally, why would they actually occur? This gets into chapter 16, which is thermodynamics, and this idea of entropy. So if there's a great increase in entropy, that will make the driving force for the reaction happen, even if it's the absorbing energy from the environment. So we'll get to it. It's this whole thing of thermodynamically favorable, right? In general, if you take entropy out of the equation, this bottom one, this endothermic thing, should never happen, right? Because why would it mix with something that it has weaker attraction to? But this idea of entropy that we'll talk about later. Don't worry about that now. Ordered. Yep. So, all right, electrolytes. Some compounds called electrolytes split into separate ions when dissolved in water. Examples are electrolytes are ionic compounds and acids. So, let us explore. Maybe. Maybe. All right. Uh-oh, it can harm my computer. It's Mr. Hamill's computer. I'll keep it. All right, I think those of you who were in Chem 1 with me have seen this before. But if I dump some salt into water and I put in a conductivity probe, what do you think will happen? It will conduct. So how can I make this light bulb brighter? Put more salt in? All right. Oh, yeah, it's brighter, 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 brighter. Yeah, I'm shaking the salt in. Yeah. What's another way I could increase the... there's one other way I can increase the brightness. Higher concentration. So take water out, I can evaporate. Whee! So... now, how can I make it less bright? Put more water back in. Now, what would happen if I let the solution out the bottom? What would happen to the brightness? Stays the same. Oh, you guys are good, right? Because I'm not changing the concentration at all. Right? I'm keeping the same concentration so it can conduct the same amount of electricity. What happens if instead I put in sugar? So dump some sugar in. Oh, darn it. Thank you. I'm dumping some sugar in. What's going to happen to the light bulb when I put it in? Nothing. All right, so let's look at what's happening on the micro scale. So if I put sodium chloride in, I get ions that split apart, right? So I have my Cl. There was just a awesome comment that sounded like it was out of like Fast Times at Ridgemont High or something. Like, nice. All right, so I can put in a lot of salt, maybe. No. I guess I can't. Here, let's reset all. What would happen if I kept putting more and more and more and more salt in? All right. So there we go. So it's only going to let me put in a little. That stinks. Okay. So they split up into the ions. Those ions can carry electricity. The most common misconception about electrolytes is that it's the metals that carry the electricity. It is not the metals that carry the electricity. It's all of the charged particles. So the pluses and the minuses are now free to move around, and both of them can carry charge. Yes? Yep. If you're what? Awesome question. So the question was about Gatorade and being on a desert island at the same time. So if you're dehydrated, you're supposed to drink Gatorade, which is electrolyte water, right? They talk about like electrolyte water. But if you're on a desert island, you're not supposed to drink salt water because it dehydrates you. It has everything to do with the concentration of those things in the materials. So Gatorade gives you like a little bit, because when you taste Gatorade, you don't taste the salt, right? So it gives you a little bit, and it's not just sodium and chloride. It gives you calcium and a few other things. But the concentration of salt water, like from the ocean, is too high. And when you get into biology, you'll learn about like osmosis and diffusion and stuff like that. So it'll actually suck water out of your cells. Now, research has shown that you can drink a small amount of salt water without dehydrating yourself. But I wouldn't do that because it tastes nasty. But you can purify the water and decrease the salt content and drink it. But that's an awesome question. It has everything to do with concentration. So now, if I put in sucrose, instead I get individual molecules. It doesn't split up into ions, right? The ions are what makes things an electrolyte, right? So here I just have my molecules of sugar. The atoms stay covalently bonded together. The water is strong enough to split up the intermolecular forces between the sugar molecules, but not the covalent bonds within the sugar molecules. Okay. And this is similar to what I showed you yesterday. If I pause it, you can see all the positive hydrogens around the chlorine ion, and for the most part, the negative oxygens around the sodium ion. All right. Okay. Okay, that was fun. Here, I want to put this here. In electrolyte solutions, solute splits into ions. Both metal and nonmetal ions can carry charge. So this is especially true in acids. All right. I was getting distracted. In acids, things like HCl, we've learned about, HCl, all nonmetals, covalently bonded together, which is true. But when you put HCl into water, because it's a strong acid, it splits apart into its ions. And now it is free to conduct electricity. Now, I always go back to the idea of the toaster in the bathtub, and I don't know why that became a thing, but like, I guess that was a high amperage device, and so I don't know how the first person decided, like, oh, you should never have a toaster next to your bathtub. Like, why would anybody do that? Anyway, there's this thing about, like, having a toaster in your bathtub. And if you're in pure water, the luxury of having toast while you bathe. So a radio I get. Like, a radio I totally understand. But anyway, so if you're bathing in pure water and your toaster fell in, you'd be okay, because pure water does not conduct electricity. But why is the water? There's two reasons why the water is never pure. You have salt from your skin. I don't care if you're the laziest, not exercisingest person in the world. You're still going to sweat. You're still going to have salt on your body. So immediately conducts electricity. There's one other reason. Thomas. Right, so when the water you get from the tap is not pure water, right? It goes through pipes, it goes through lots of stuff. It absorbs CO2 from the atmosphere, absorbs lots of stuff from the atmosphere. There's iron and stuff. We fluoridate our water to protect our teeth. We'll talk about that later in the year too, which I think is really neat. So there are ions already in the water when it goes into the bathtub. So yeah, don't eat your toast in the tub if you're gonna cook it right next to it. All right. So anyway. Solvation shells. We already talked about this, but this is the water molecules that surround an ion. So just going back, this is at this point it's stuff you've already. You know what? I'm gonna make it different. I'm tired of sodium chloride. Let's do the acid one. No, let's not do the acid one. We'll make it. Oh, that's not what I wanted to do either. Oh yeah, the shamrock color. All right. I don't know what coral is. Oh, Sammy. Oh, okay. Well, next time I'll do coral. I'm going to do shamrock. All right. So, how would expect to have to do this at some point on a quiz or test or something. How would the water molecules align around lithium? What part of the water molecule would be attracted there? Dan? Yeah. So you get like these 6 water molecules. And this is a terrible drawing. But you get multiple water molecules that surround your lithium ion. You don't have to draw all the partial negatives or partial positives. It's going to take up too much space. So again, we go back to like our fundamental ideas of Coulomb's law and opposites attract. And then here it would just be the H's. You might even have both sides attracted. All right. So just think opposites attract. An ion. All right. So non-electrolyte solutions are not ionic compounds and they're not acids. So how must they be held together? What sort of bonds hold non-electrolyte particles together? Not everybody all at once. They're not ionic or acidic. And they're not metals either. Covalent. Which means they are molecules. Right? So the individual molecules remain intact. The IM forces between them are disrupted. And this is almost always hydrogen bonding or dipole-dipole in water solutions. The ion forces between molecules is disrupted. That's why if you put sugar in water, you can taste the sugar, right? Because those sugar molecules stay the same. Sugar stays sugar, just separated from other sugar molecules, like we showed. So really you have to think about what type of bonding is present to determine if it's an electrolyte or non-electrolyte solution. We're going to avoid the acids for the time being in terms of worrying too much. We're not going to expect you to be able to identify an acid yet, right? Maybe on the problem set there might be one, but that's it. All right. We're going to do 2 more slides in the next 3 minutes, because I feel like I'm not going quickly enough, which is okay. I'm having fun. I know everybody is out there at home. At some point, I'm just going to, like, I don't know, give random messages to people in the middle of lecture and see if they pick up on it. All right. So, molarity. We talk about molarity. This is how we measure concentration. There's lots of other ways to measure concentration, but this is the one we're going to use. They took out the other ways from the AP curriculum. Things like molality, mole fraction, mass fraction. You don't need to worry about those. You need to worry about molarity, which is big M equals moles of solute divided by liters of solution. Now, the biggest mistake people make is this is not liters of solvent. It's liters of solution. The solute takes up space. For example, if you dumped a bunch of salt into 100 milliliters of water, you would no longer have 100 milliliters of water. You'd have slightly more than 100 milliliters of water. So we measure the molarity in moles of solute per liter of solution. So, for example, if I have 0.1 moles of NaCl in 500 milliliters of solution, what's my molarity? Who can do fast mental math? Yeah, my molarity would be 0.2. So really the way we would say that is 0.2 m. So 0.1 moles divided by 0.5 liters, we have our molarity. And I'm actually going to stop here.